Section 8.4, Demouvre's theorem, powers and roots of complex numbers. So to start this section off, I want to talk about r cos theta plus I sine theta squared. This is one of the cases that I get for Demouvre's theorem, but we're just going to work it out. Now, I don't want to do where it's to the fourth or to the fifth power, because that would be a whole lot of work. We're just going to do squared because I just want you to see how nicely this actually works out when we use this theorem. So we're not going to use it right now. We're just going to do everything by hand. So my first step then is I'm just going to take r squared and then cosine theta plus I sine theta squared. And then from here, I'm just going to show you how I get the cosine of theta plus I sine theta times itself twice, because I want you to see where this is all going to come from. Now I'm going to FOIL this out. So that's going to be cosine squared theta, I sine theta, cos theta, plus I sine theta, cos theta, plus I squared sine squared theta. So now from here, I'm just going to combine like terms and simplify wherever I can. So it's going to be 2 I sine theta, cos theta. And notice here, I have a negative sine squared theta. And if you look at this, I get I squared, and I squared equals -1. So that's why I get negative sine squared for that one. Now what I'm going to do from here is I'm just going to rearrange my trig functions here. And the reason why I'm doing this is because I'm setting it up to use trig identities. So this is what I end up with. Now, if we know our trig identities, you'll know that those two together equal cosine of 2 theta. And then if I put, oops, I forgot something here. I forgot my 2. And if I put those together, that's also going to be, well, that's not also going to be, but it's going to be sine of 2 theta. So that's what I end up with here for those two. So now, when I write this all together now, this is going to equal r squared cosine 2 theta plus I sine 2 theta. Now what's interesting about this is when I square it, I get my r squared here. That same 2 I see in here and in here. So it always works out very nicely that way. And that's the crazy thing about this. With the I squareds and all those things coming out, it really makes this work nicely. So when I'm taking this complex number here, now remember, don't forget about this. That is a complex number, and I square it. This is my end result down here. Now, I wouldn't have to go through all this work all the time, but definitely I could use this theorem now. Let's take a look at the theorem. So here it is. Demouvre's theorem says if r cos theta plus I sine theta is a complex number, and if n is any real number, then the following holds. So notice this. What we had is we had this 2 here. That was this power here, and they said, hey, it's going to be r to the n cosine n theta plus I sine n theta. And if you look at what we have up here, that's exactly what we have here when we actually worked it out. So we don't have to work this out all the time. Demouvre's proved this for us. So now we can use this theorem. And even simpler, take a look at this one here. Sometimes I can write it in that simplest form that way. And this is a huge benefit for us. And the reason why is because when we deal with some of these complex numbers, we're not going to want to deal with them in this rectangular x and y form. Because of this theorem, we're going to want to turn it into Rn cis n theta, or I should say r cosine theta plus I sine theta, so that we can actually just do the power very easily. And that's what we're going to do now. So now this problem says find 1 plus I square root of 3 to the 6th power and write the answer in rectangular form. So now if I had to write this out, six times and actually multiply it out, that would take me forever. So there's an easier way to do this. If we can turn this into r cosine theta plus I sine theta, then we can use this theorem. So that's what we're going to do. So the first thing I'm going to look at is finding the r here. So that's going to be 1 squared plus negative square root of 3 squared equals r squared. And then when I do this, I'm going to get 1 plus 3 equals r squared. And then I'm going to get r squared equals 4, and then r equals 2. So I get r equals 2 this way. Now I'm going to have to find my theta here. So again, I always have to keep in perspective here what quadrant I'm in. So I'm in the fourth quadrant because I'm going to the right one and down square root of 3. So I'm going to be over here. And I know that my x, and this first number is my x, is going to be 1. And my y is going to be negative square root of 3 because this is my y on the imaginary part. And then I know from this is my special triangle because that's now going to be 2. Or I could use the Pythagorean theorem if I didn't catch that. So I know this angle here is 60 degrees. So if I'm thinking about it in terms of the other angle there, I could call it a positive angle if I wanted to, because if I went in this direction, I would have to say negative 60 degrees. If I went all the way around, I would say 300 degrees. So we'll just use the 300 degrees. Actually, the negative 60 probably wouldn't be bad either. So I don't know. We'll try both, maybe. We'll see. So theta is 60 degrees, negative 60 degrees, or 300 degrees. So then what does that mean for us? So it means I have 2 cosine of negative 60 degrees plus I sine negative 60 degrees. And that is going to be to the 6th power. So now what I'm going to do from here, oops, I put an extra, no I didn't. I thought I put an extra parenthesis in, but I didn't. Okay, so now what I'm going to use is I'm just going to use his theorem. So that means this is going to be 2 to the 6th. And then cosine of 6 times negative 60 degrees plus I sine of 6, because remember 6 is my n here, so just kind of keep that in mind there. And that's where that 6 is coming from. 6 times negative 60 degrees. Oops, I was trying to do a theta there. So that's what I'll end up with right there. Yep, I put too many in that time. Oops. So there it is. Hopefully you can see that okay. All right. So now we can just multiply those out. So then that's going to equal 2 to the 6th. 64 times negative, oops, I forgot to put my cosine in. Cosine of negative 360 degrees plus I sine negative 360 degrees. So then this actually becomes very easy, because this here, cosine of negative 360 degrees, is actually, if we think about it, that's going to be here. And I know the cosine there is 1, and the sine there is 0. So we're going to actually get 64 times 1 plus really 0i, and I'm just going to put that in for now, just so you can see it, because sine of negative 360 is 0. That goes away, really, and I get 64 times 1, which is just 64. So there's our answer. Now, if I did it the other way, I would have the same result. I'd be multiplying a larger number there. But if you think about this, that would be 300 times, because if I use the 300 degrees instead of the negative 60, then that would be 300 times 6. And 300 times 6 would be 1,800. And 1,800 actually can be divided. Well, I can, 360 actually divides 1,800, so that would really take me back to the same place. So it doesn't really matter which one I use here, but I just kind of wanted to show that to you of where that comes from. So it's 64. So that's the beauty of this theorem. If I had to work it out straight away, like this way, and just multiply it out 6 times, that would take me forever. This wasn't bad at all, so it's a nice theorem.